80 kilogram block is pushed up an inclined plane with a kinetic coefficient of friction of 0.70. The angle of the incline is 25 degrees. The applied force pushing the block acts at an angle of 35 degrees with respect to the horizontal. What is the applied force required to push the block up the ramp at a constant velocity? So I've done one similar to this problem before, where there's a force pushing the block up the ramp, but notice how it's diagonal with respect to this horizontal dashed line. So it acts at an angle. Before I called this the force F, and I called the angle theta with the subscript F, which is a great way to label it. But I'm just going to call it phi, so I can really distinguish it from my other angle. Now I'm going to draw the components of this vector. Here's my amount of F in the x direction, so that's along the horizontal. The amount of force in the vertical y direction is Fy. That's a little, should have left more space, but that's good for now. Okay, and again, there's going to be a normal force acting on the block. That's the force of the ramp pressing against the block. If you're on a surface, you always have a normal force. Now the block is being pushed up the ramp, so the acceleration we draw in this direction to specify the motion. So if motion occurs to the right, due to the force F, then friction occurs to the left, which opposes the direction of motion. So this is the friction here. Next, there's weight, which acts straight down, which is also called force due to gravity, or simply gravity. But this also has components. So I'm going to break this W vector into two pieces. This is going to be the amount of weight acting in the y direction. It should be perfectly across. It should be opposite from the normal force, and it should be equal in magnitude. So I'm trying to draw this next purple vector with an equal length to that of the n vector. My wy should be equal and opposite. And then here's my wx, the amount of gravity pulling you down the ramp. Finally, the angle inside this triangle formed by the gravity vectors should be the same as the angle theta, the angle of the ramp. So finally, you do have the mass, which is the 80 kilograms. The Greek letter mu with a little subscript k represents the kinetic coefficient of friction. We labeled the angle of the ramp theta, that's at 25 degrees. We labeled the angle of the force phi. Some people pronounce it phi, but it's more appropriately called phi. Now, what is the force required to pull the block at a constant velocity? Constant velocity means acceleration is 0. And our goal is to find the applied force. So find F. So we apply Newton's second law in the x direction. Sum of all forces acting horizontal equals mass, horizontal acceleration. What are all horizontal forces? Well, we have an F, an Fx, and a Wx. So I'm going to write those down. The horizontal forces would be the applied force in the horizontal direction, the friction, which is negative because it points left, and Wx points left, equals 0 because it's mass times acceleration, but acceleration is 0. So now I replace each quantity. I know friction has a set in stone formula. It's always mu k times n. And on an inclined plane, we know that Wx or in general, we know W itself equals mg. So furthermore, Wx should be W mg times a factor of sine, whereas Wy equals W or mg times a factor of cosine. So I'm going to replace each quantity. I know Fx, the little x indicates multiply my force by a factor of cosine. So that's F cosine phi minus mu times n for friction minus Wx, which is mg sine theta, and the right side equals 0. Now, the first step is complete. You should box this equation. This is your equation 1. Now, I've developed the habit recently to immediately remind myself of what we're solving for, which is the variable f. So sometimes I like to actually isolate f at this step, but it's actually better to leave it be. And we'll see why. Because although you could isolate f now, when we derive an expression for normal force, that's also going to contain f. So we don't want to isolate it, because then we'll just have f's floating around everywhere, and it's going to be extremely confusing. So again, notice how I immediately recognized our next step is to solve for normal force. And if you watched my other videos, I make that such a recurring theme to identify that pattern. We don't know normal force. So to find it, you apply Newton's second law in the vertical or y direction. All vertical forces, there's a normal force, weight in the y direction, applied force in the y. Now the block is not vertically lifted off the ramp. No motion occurs in the y direction. 99% of the time, that's your next step. So again, we get 0. So normal force minus mg cosine theta plus Fy, that would be F cosine phi. Oh no, F sine phi. And this is equal to 0. Perfect. And let me isolate n now, because that is our goal. So n would equal mg cosine theta. I add that to both sides, minus F sine phi. This is equation 2. Perfect. So here's the pattern. we do isolate n, we want to derive our own equation for n. Then we plug this expression, we substitute this expression in place of n for equation 1. So if we go back to equation 1, it said we had f cosine phi minus mu times normal force, but I'm replacing normal force with the expression mg cosine theta minus f sine phi. Then it said plus, or no, minus mg sine theta equals to 0. So that's what we had. Okay, perfect. Now I see there's multiple f's floating around, as I mentioned. So let's distribute this term. We'll get f. Actually, let me leave a little bit of space here. We'll get f cosine phi minus mu k mg cosine theta plus, because we're distributing a negative to a negative, mu f sine phi equals, I'm going to add the mg sine theta to the other side so we could start isolating f. Now f appears in both terms. We can factor it out. So that way we have one f floating around to isolate. If I factor out f, I'm left with the cosine phi plus mu k sine phi. And I'm going to add this term to the other side. Because again, I want to move everything away from f. So I'll still have my right side plus my other term. Perfect. Now, once we divide both sides by the expression in parentheses, we have solved for f. And you can do one more step to save you time on the calculator. mg appears in both terms. You can factor that out as well. So we get f would be, factor out the mg, we're left with sine theta plus mu cosine theta divided by everything in the parentheses. So that would be divided by the cosine phi plus mu sine phi. Final answer. Perfect. Some physics classes that would be done for this particular situation, that's the equation for f. Wonderful. So we're basically done, but let's plug in the numbers. So now I'm just going to do f equals. So it was mg, so I'm going to replace my m with 80. G is 9.81. We said sine of theta, so that's sine of 25, angle of the ramp, plus mu, 0.70, cosine, angle of the ramp. Now I'm just moving a little faster because I'm rewriting. So if I'm speaking fast or anything, just feel free to pause the video. Again, the denominator was cosine phi, so cosine 35 degrees, the angle of the force, plus mu sine angle of force. Let's find out what the numerator is. So the numerator is about 829.6. So see if you could get that in your calculator. And then for the denominator, I get about 1.22. So after you divide that, your final value for force is around 680 newtons. Final answer. So that's how you calculate the magnitude of force pulling a block up a ramp. I really love this problem. I think it has beautiful algebra. It really captures what it means to do physics. I like how we had to interpret the problem and know that constant velocity means no acceleration. Because again, acceleration means change in velocity, but there is no change. It's not speeding up nor slowing down. So that's a great method on solving problems with an inclined plane. Now, even if the quantity they ask for changes, then only the algebra changes, but the process remains the same. And that's what I want you to take away from this video.